자, 그러면 이번 시간에는 Basic Pricing Equation 두 번째 부분 진행하도록 하겠습니다. This lecture is about the second part of the Basic Pricing Equation. Let me share the screen. So what kind of payoff will be priced high? So that is the central question in asset pricing. So given the stochastic discount factor that supposedly prices all assets in the economy, we want to know how prices at current period is determined. 자, 그러면 stochastic discount factor가 주어졌을 때 이 stochastic discount factor가 다른 여러 가지 에셋들을 어떤 식으로 프라이스하는지, 즉 어떠한 에셋들이 가격이 높게 설정되고 어떠한 에셋들이 가격이 낮게 설정되는가? That is the central question in asset pricing. And according to the pricing equation that we learned in the last time, the stochastic discount factor, or MT, is going to put more weight, in other words, give more value to an asset that has higher payoff xt plus 1 when mt plus 1 is high. 즉 무슨 말이냐면요. 이 stochastic discount factor는 어떤 에셋이 페이오프가 stochastic discount factor가 높은 스테이트에서 더 많은 페이오프가 나올 때 그러한 에셋에 더 많은 가중치를 부여해서 가격을 높게 설정하게 됩니다. 자, 이것을 어떻게 이해할 수 있냐면요. To understand this, let's take a look at the following equation. In the following equation here, you can see that the price, the current price, according to the pricing equation that we learned last time, is the expected value of the product between M and X. 그래서 두 가지의 밸류를 곱할 때 어떠한 프로덕트가 더 많은 페이오프를 내겠어요. 즉 M이 높을 때 X 또한 높은 값을 가지는 경우. 무슨 말이냐? M이 높을 때 X 또한 높은 값을 가질 때 그러한 에셋들이 더 높은 가격을 형성하게 되는 거예요. In other words, when M is high and X is high, in that cases, such asset P of whose payoff is xt is going to have high prices. To see that mathematically, you can decompose the product of the expectation into these two components. Why is this the case? That is because we know that covariance between two random variable is mathematically equal expectation of x times y minus expectation of x times expectation of y. Okay, and then you rearrange the thing and then you get this equation here. In other words, when is the price going to be high? That is when the covariance between the two is high. In other words, for an asset that has high payoff, when M is high, that such asset will have higher prices as well. Okay. 즉 무슨 말이냐? Price PT is going to be high if the asset pays off more in the future state when MT plus 1 is high. So if you have two different stocks, one stock pays off when M is high, the other pays off when M is low. Which of the two stocks will have higher prices? The one that pays off high when the stochastic discount factor M is also high. Okay. Then the crucial question here is, in which state MT plus 1 is going to be high? 자, 무슨 말이냐면 결국 자산 가격이 어떻게 결정되냐는 자산 가격의 페이오프, 그 자산의 페이오프가 스토캐스틱 디스카운트 팩터와 어떻게 코베리 하는지가 중요한 거예요. 즉 어떠한 스테이트에서 스토캐스틱 디스카운트 팩터가 높고 그 스테이트에서 어떤 에셋이 어떻게 페이오프 하는지가 가장 중요한 것이 되게 됩니다. To understand that, we need to look at the stochastic discount factor again. So in the model that we saw before, stochastic discount factor is simply the ratio of two marginal utilities, or this is the marginal rate of substitution. 즉, stochastic discount factor는 지난 시간에 봤듯이 marginal utility의 비율로 구성이 되죠. 밑에 먼저 분모를 봅시다. Let's take a look at the numerator. I'm sorry, denominator. This denominator is a constant. This is included in the current information set. 분모는 타임 t에서는 이미 알려져 있는 변수죠. 따라서 이 변수 분모는 상수이기 때문에 stochastic discount factor의 미래의 realization에 전혀 영향을 끼치지 않아요. 자, 그러면 모든 uncertainty는 전부 다 future consumption에서 보이죠. All the uncertainty is coming from the future marginal utility because this is the random variable. This is the thing that concerns us the most. Now, remember that utility is a concave function, meaning the second order derivative is a negative number, according to the Jensen's inequality. Therefore, future marginal utility is a decreasing function in C. 즉 무슨 말이냐? 2차 도함수가 음수이므로 1차 도함수는 어떻게 되겠어요? 1차 도함수는 this is a decreasing function in C. 즉 따라서 C가 증가하면 증가할수록 무슨 말이냐? This marginal utility function is a decreasing function in C. In other words, when C is high, when consumption is high, future consumption is high, what happens to the marginal utility or the stochastic discount factor? This is going to be high. I'm sorry, this is going to be low. When CT plus 1 is low, the marginal utility is going to be high. 즉, when consumption is high, when future consumption is high, and what kind of state is it? When future consumption is high, 미래에 소비가 많을 때 어떤 때겠어요? 어떤 때 우리가 미래에 소비를 더 많이 하겠습니까? 호경기일 때. When things are good, when the economy is expanding, when people can consume more, 그때가 호경기죠. 이러한 호경기일 때 stochastic discount factor는 그 값이 낮게 돼요. In other words, when things are good, stochastic discount factor is low. 그에 반해서 불경기일 때 when things are bad, consumption is low and the stochastic discount factor is going to be high. Okay? So the stochastic discount factor captures the economy, the state of the economy in an opposite way. So when things are good, stochastic discount factor is low. When things are bad, stochastic discount factor is high. 불경기, 즉 경제 성장을 안 하거나 아니면 소비자들이 이제 소비를 많이 못할 때 이럴 때가 바로 stochastic discount factor가 높고 경기가 안 좋을 때예요. 그리고 소비자들이 컨숨을 많이 할 때는 stochastic discount factor가 낮고 이럴 때가 바로 경기가 좋을 때 when things are good. So when does this happen? In what state of the economy? It's the state of the economy when things are bad or the stochastic discount factor is high. So what are the examples of assets that pay well when the future marginal utility is high? 미래의 marginal utility가 높을 때 xt plus 1 이 높은 asset이 어떤 것일까요? So what kind of assets will have high future payoff xt plus 1 when marginal utility is high? In other words, bad states. When things are bad, what kind of assets will pay high when things are bad? Can you imagine some? Safe assets. 아니면 gold, 금. Or 무위험 채권들, riskless assets. For example, like U.S. Treasury bonds. 미국 국고채. 미국? These kind of assets will pay well when future marginal utility high. Therefore, their prices are high. Well, you can think of gold. Why is the price of gold so high? Because gold is a safe asset. It's an asset that pays off well when future economy is bad. Now, we can rewrite the previous pricing equation in terms of gross returns RT plus 1. In other words, from the previous pricing equation, let's just divide both sides by PT, the current price. Because the current price PT is a known constant, it can go inside of the expectation. 자, 무슨 말이냐? 그 전에 베이직 프라이싱 이퀘이션이 이렇게 주어졌잖아요. 이렇게 주어졌습니다. 자, 양변을 PT로 나눠볼게요. Let's divide the both sides by PT. Okay. Now this expectation is taken in terms of information set FT. In the information set FT, this PT is just a constant. In other words, constant can just simply go inside of the expectations operator. It can also go out of the expectations operator. Now, once you put PT inside, then you have the following, right? This item just becomes the future return. In other words, this is the new pricing equation, new return equation. Why do we want to deal with returns instead of prices? Because returns are much easier to deal with in empirical applications as returns are stationary while prices are explosive. This is a very important concept. 왜 우리가 리턴으로 프라이싱 이퀘이션을 볼까요? 그 이유는 리턴이 통계적으로 훨씬 다루기가 쉽습니다. That's what's called the stationary property. Returns, because returns are usually assumed to be stationary, returns have well-defined second moment, first moment, and so on. So returns, for returns, you can estimate mean and standard deviations very easily. But for prices, they are explosive. 무슨 말이냐? 어떤 회사의 주가를 보세요. 주가는 explosive하게 돼 있습니다. price. 그래서 통계적으로 이러한 explosive process 같은 경우는 통계적으로 아주 다루기가 어려워요. 그래서 우리가 리턴을 사용합니다. 리턴을 사용하게 되면 어떤 일이 발생하게 되냐면 평균 중심에서 움직이죠. 이러한 성질을 우리가 스테이셔너리하다고 그래요. 스테이셔너리한 프로세스가 훨씬 다루기 수월합니다. And we also consider the item called excess returns or payoff to a zero cost portfolio, which we call usually RE, which is simply the difference between two returns, RA and RB. 때로는 excess return이라고 해서 제로 리턴 포트폴리오의 페이오프가 되겠죠. 이거를 사용하는 경우가 많은데 이 excess return은 무엇이냐? 두 가지 다른 리턴의 디퍼런스입니다. 그래서 어떤 두 가지 리턴의 디퍼런스냐? 보통은 이제 예를 들면 뭐 스탁 마켓 리턴에서 리스크 프리 레이트를 뺀 경우 이런 경우가 돼요. Why is this excess return important? Because excess return can be thought of as a payoff to a long short strategy. So you invest $1 in an asset A and short sell the other asset B. 즉 이 excess return은 어떤 의미를 가지냐면요. long short strategy, long short 하는 투자 전략과 같은 종류의 리턴을 가져오게 돼요. 즉 앞에 있는 여기 이 같은 경우에는 A라는 리턴을 long 하는 거고 B라는 리턴을 short 하게 되는 거예요. 자, for managed portfolio return, we just multiply ZT in front of RT plus 1, where ZT is an investment strategy based on information available at T. Then price of this strategy is simply ZT. And ZT is sometimes called instruments, which we will cover later in later lectures. Now let's take a look at risk-free rate, 무위험 자산이율. Suppose we price a risk-free asset known at T. Risk-free asset is always known at T. So I will not use T plus 1, but instead I will just call it T. And then this risk-free asset should also be priced. So I will just include it in the return pricing equation that we saw in the previous slide. 자, 앞에서 본 return pricing equation이 어떻게 되었죠? return pricing equation이 이렇게 주어졌잖아요. 이렇게 주어졌으니까 여기에 RT plus 1 대신에 그냥 risk-free rate를 넣은 거예요. Why? Risk-free asset is also traded asset, so it should also be priced. risk-free asset에 대해서도 이 pricing equation이 성립해야 되니까 because the risk-free asset should also satisfy the pricing equation here, so we can just simply plug in and get this expression. And because risk-free rate is a constant, it can come out of the expectation operator. Why is the risk-free rate constant? Because it is known at information set T. Okay. So it can come out of the expectations operator, and therefore we get the following. In other words, in economy, risk-free rate is not a arbitrary number, but it is determined by the stochastic discount factor. And for the case of the power utility function, so what was the power utility function? 파워 유틸리티 같은 경우에는 이게 어떻게 정의가 됐죠? 이렇게 정의됐잖아요. In the case of the power utility function, plug it in and you get this expression here. So based on the pricing equation, we can understand how risk-free rate or interest rates are determined in the economy. And let's see how that is going to happen. 자, risk-free rate과 consumption growth. Consumption growth는 this can be viewed as the ratio between future consumption and current consumption. 즉 경제가 얼마나 빨리 성장하고 있는지 아니면 소비자들이 얼마나 많은 양을 더 소비하고 있는지에 대한 measure예요. 즉 consumption growth is a very good measure of the state of the economy. And risk aversion. Let's see how these three quantities are related. 즉 위험 회피 계수가 뭐죠? In the case of the power utility is gamma. Consumption growth is CT plus 1. The ratio between CT plus 1 and CT. And the risk-free rate is simply RF. Let's see how these three things are related in the economy. So from the previous slide, we have risk-free rate as given as 1 over beta. I mean, what was beta? Beta was the discount factor, right? How investors discount future utility with respect to the current utility. We're not going to focus on beta here because beta is not a very interesting parameter to consider. 자, 그러면 베타에는 집중하지 않고요. 왜냐면 베타는 경제에서 별로 큰 의미를 갖는 상수는 아니에요. 따라서 consumption growth. What is in the utility function? 이게 consumption growth죠. 그리고 consumption growth, 그리고 risk aversion, and the risk-free rate. 이 세 개가 어떻게 결정되는지 봅시다. 자, risk-free rate는 왜 중요하냐? 이거는 이자율로도 볼 수 있어요. It can be viewed as interest rate. Interest rate RF is going to be high when consumption growth is high. 여기 방정식에서도 볼 수 있듯이 consumption growth가 높을 때 이자율이 높게 되죠. When is that going to happen? Why is that going to happen? I'm sorry. 자, 다음과 같은 경우를 생각해 봅시다. When future consumption is expected to be high, when is that going to happen? 미래 스테이트가 좋을 때, 경제가 발전할 거라고 생각하고 미래에 돈을 더 많이 벌 거라고 생각할 때 컨숨을 더 많이 하겠죠. 미래 소비가 늘어나게 됩니다. 즉 경제가 더 발전할 것 같고 미래에 더 소비가 많을 것 같을 때, 자, 그러면 여러분들이 투자자라면 어떻게 하겠어요? 미래에 더 소득이 많고 미래에 더 컨슘을 많이 하기 때문에 현재 컨섬션을 늘리기 위해서 미래 소득에 대비해서 대출을 일으켜서 현재 소비를 더 늘리게 됩니다. 그러니까 어떤 경우를 생각하시게 되냐면 Suppose you are young, 20대라고 생각해 보세요. 20대는 소비를 많이 못하죠. 30대, 40대, 50대에 비해서. 즉 그러니까 20대에는 학자금 론도 대출받고 뭐 담보 대출도 받고 무담보 대출도 받아서 current consumption 레벨을 높이고 대신에 미래에 더 빚을 갚아나가게 되는 것이죠. So when enough investors are doing that, when enough investors are borrowing against future to increase current consumption, why is that happening? Because you are going to earn more in the future. So there will be demand for loans. Therefore, the interest rate is going to be high. 즉, 현재 소비 수준이 낮고 미래 소비 수준이 높을 때 어떻게 하겠어요? 미래 인컴에 대해서 대출을 일으켜서 현재 소비를 더 높이려고 하겠죠? 자, 대출 디맨드가 많으면 대출에 대한 수요가 많으면 어떻게 됩니까? Interest rate is going to be high when the demand for risk-free rate is high. That's the first channel that we can consider. In the second way we can interpret this equation is the following. When interest rates are high, suppose the left-hand side, RF is high. Now, what are you going to do? Investors want to consume less today and invest more in the future so that they can consume more. They invest more today so that they can consume more. 무슨 말이냐? 이자율이 높으면 오늘 컨숨을 하고 싶은 인센티브가 낮게 돼요. 왜냐면 오늘 내가 컨숨을 안 하고 은행에 그 돈을 넣어두면 이자율이 높으니까 내년에 그 돈이 더 많은 수익률이 높게 되겠죠. 수익률이 높아서 미래에 내가 더 소비를 더 많이 할 수 있게 돼요. 따라서 consumption growth가 높게 됩니다. In other words, this channel just is saying that when the risk-free rate is high, consumption growth, when risk-free rate is going to be high, consumption growth is going to be high. But what the first one is saying is that when the consumption growth is high, 즉 미래의 소비가 훨씬 더 많을 때 현재 소비에 대해서 여러분들은 현재에도 더 소비를 하고 싶죠. 따라서 대출을 너무 많이 일으키니까 은행에서는 이자율을 높이고 싶겠죠. So either way, you can understand the equation. In other words, there are two side effects when future consumption is high, that is going to create current interest rates high. In the opposite side effect is that when interest rates are high, investors want to invest more so that they can consume more tomorrow, so that consumption is also high. Now, let's take a look at the effect of the risk aversion on the risk-free rate. Risk-free rate is going to be more sensitive to consumption growth when risk aversion is large. 즉, risk aversion coefficient가 높을 때 consumption growth가 변하면 risk-free rate이 더 심하게 변하게 돼요. But you can see that easily mathematically. When risk-free rate is when risk aversion is high, okay. 자, risk-free rate과 consumption growth 사이의 관계를 보면 감마가 낮을 때는 when risk aversion is low, the slope is rather moderate. But when risk aversion is high, effect is creating is that this, okay, as gamma increases. Okay? So in other words, for a given change in the consumption growth, when gamma is high or the risk aversion is high, interest rate is going to change by a much larger margin. So in other words, when gamma is high, when gamma is large, therefore utility is more highly curved, the investors care more about the maintaining a consumption profile that is smooth over time and is less willing to rearrange consumption over time in response to interest rate incentives. 자, 이게 무슨 말이냐? When gamma is high, investors are very risk averse, meaning that they want to smooth their consumption profile more, even when there's interest rate changes. Therefore, even when gamma is high, given a greater interest rate changes, the corresponding consumption growth change is going to be little. Therefore, it takes a larger interest rate change to induce the investor to a given consumption growth. 자, 리스크 어버전 코에피션트가 높으면 어떤 일이 발생하게 되냐면요. 리스크 어버전 코에피션트가 높으면 인베스터들이 인트러스트 레이시, 자, 이자율이 변하게 되면 투자자들이 돈을 이제 뱅크에 넣고 아니면 뭐 스탁마켓에 넣고 해서 오늘 할 수 있는 투자를, 오늘 할 수 있는 컨섬션을 미래로 미루게 되죠. 왜냐하면 지금 은행에 돈을 넣으면 이자율이 높으니까 거기에 따른 수익률에 의해서 더 많은 소비를 할 수 있게 되고요. 그런데 when investors are more risk averse, they don't want to change their consumption profile too much because they are very risk averse. So even when interest rate changes a lot, they don't want to change their consumption growth profile. Therefore, it takes a larger interest rate change to induce the investor to a given consumption growth when risk aversion is high. Okay. So let's take a look at this example of log normal consumption growth. Suppose that consumption growth is log normally distributed. Remember, we have log normal distribution here. In other words, log of the consumption is going to be random variable, defined as the normal random distribution. Okay? And we know from the previous result that when some variable z is normal random variable, the exponential of z is going to be given like that. Okay? Now let's solve the following equation here. 자, 이거를 직접 데리베이션을 해봅시다. 어떻게 되는지요? 먼저 위에 있는 이 이퀘이션이 앞에 있던 오일러 이퀘이션이잖아요. Now, you can see that the beta times the consumption growth to the negative of the gamma power. 자, 이렇게 쓸 수 있죠? Okay. So e to the log, natural log beta minus gamma, and I'm going to use the following notation here. Delta of log ct plus 1. Okay? So what am I defining here? So log, I'm just writing as log ct plus 1. Okay? I am going to define it as lower capital letter. 소문자 ct로 정할게요. 소문자 ct plus 1. Then log of ct plus 1 over ct is log of ct plus 1 minus log of ct. So this is, in a lower capital letter. And this is delta ct plus 1. Okay? So okay. So without using this, without using the lower capital letter, if I just keep using the upper capital letter, 대문자로 계속 할게요. 대문자 ct plus 1으로 하겠습니다. 그럼 대문자로 표시하면 어떻게 되겠어요? 대문자 ct로 하면 이게 log, I'll just write it as log ct plus 1. Okay? So 이게 여기 이게 되는 거고요. In other words, okay, let me use different color. So this term here is going to be this. Okay? 그리고 plus rf. Okay? And I am defining log of rf as lower capital letter rf. Okay? Now, if you look at this, 여기를 보면요. Okay? 이 amount가, this term is what is in the expectations operator here. 근데 여기 있는 게 저기 있는데, 자, 여기서 봅시다. Which one is random and which one is constant? What about log of beta? This is constant, right? So this is constant. Risk-free rate is also constant. The only randomness here is this thing, right? In other words, if you take the expectations operator here, so expectation of e to the log beta minus gamma delta log ct plus 1 plus rf. 자, 여기와 여기가 constants죠? So they can come out. They can come out. Okay, they can come out, and it becomes e to the minus gamma delta log ct plus 1. Okay. Now, given that this thing here is a random variable, it is a random variable, normal random variable, and let's just call it with mean m and variance sigma squared. Okay. So in other words, delta log ct plus 1 is a normal random variable like this. Okay, let's just suppose that's the case. Then what do we have here? Finally, it's the log of beta plus rf times e to the minus gamma of m plus a half of the gamma square sigma squared. Okay, and this is the reason is that because when the delta log m log ct plus 1 follows the normal random variable of m and sigma squared, the gamma times log of delta c plus 1 follows normal random variable with mean of negative gamma times m and gamma squared sigma squared. Okay, so if you remember the result that we learned about the log normal random variable, this is what you get. Okay, so this is the average, and this is the half of the variance. Okay. Okay. So, and we know this should be the same as 1. Okay, that should be the same as 1 here. Therefore, if you take log on both sides, what happens? 0 equals log of beta plus RF minus gamma m plus a half of gamma squared sigma squared. Okay, and you, by rearranging the terms, you get the equation here. Okay, a beautiful mathematics, right? 자, 이런 같은 데리베이션 다음에 다음과 같은 식이 나왔죠. Risk free ratio 어떻게 결정되냐? Negative of the discount rate. So when beta is high, risk free rate is going to be low. Okay? In other words, when discount rate is high, when beta is high, investors don't discount much about the future consumption. Therefore, risk free rate is going to be low. What is important for our purpose is that these two terms, okay, these two terms. First of all, when consumption growth rate is high, in other words, what is consumption growth? Okay. In terms of log transformation, this is delta log of right? 자, 이게 consumption growth죠. 이게 consumption growth고, consumption growth is when consumption growth is high, risk-free rate is high. Okay. Does it remind you of something? Yeah, that's exactly what we learned here. When consumption growth is high, risk-free rate is high. Okay. When consumption growth is high, risk-free rate is high. It's the same equation. The only difference is that we began from the same equation, right? 똑같은 equation을 이용했어요. 즉 여기서부터 바로 앞에 있는 슬라이드에서는 이 이퀘이션을 가지고 바로 우리가 유출을 했었는데 지금 원래는 이제 expectation operator가 있으니까 사실 앞에 있는 여기 슬라이드에서는 우리가 CT plus 1이 constant라고 assume을 하고 expectation 없앤 거거든요. Here we are assuming CT plus 1 is a constant. Therefore, we didn't take the expectation. But that is not exact. So to do it more precisely, what do? We assume the distribution for consumption growth. 앞에 있던 analysis, 그 전에 있던 analysis를 보다 더 정확하게 하려면 expectation operator를 풀어야 돼요. 즉 평균을 구해야 됩니다. 근데 distribution을 모르면 평균을 구할 수가 없으니까 우리가 distribution을 assume 한 거예요. 어떻게 assume 했죠? distribution이 normal random variable이라고 assume을 한 거죠. 맞죠? Log of CT plus 1 over CT is a normal random variable. In other words, the consumption growth is log normally distributed. 그러한 가정 하에서 우리가 이런 이퀘이션을 뽑아냈어요. 즉, in other words, the interpretation of the previous slide should be the same as the interpretation that we get out of here. 즉, 어떻게 되냐? consumption growth가 높을 때 risk-free rate이 높게 되죠. There's one more effect here. This is the effect. When the volatility of the consumption growth is high, 즉 investor 경기가 훨씬 더 불안정할 때 risk-free rate이 낮아지게 돼요. 즉 when volatility of the consumption growth is high because of the negative sign here, risk-free rate is going to be low. 즉 volatility of consumption growth가 높을 때 경제가 더 불안할 때, 경제가 불안할 때 컨섬션이 막 변하겠죠. 경제가 불안할 때 risk-free rate이 더 낮아지게 됩니다. Why is that the case? Because investors want to save more. Investors want to save more. That is what's called the precautionary saving. 경제가 불안하면 은행에 더 많은 돈을 넣어두고 싶어요. 왜냐하면 나중에 경제가 안 좋아졌을 때 현금이 필요하니까요. 그러한 precautionary saving, 저축에 대한 위험 회피를 위한 저축에 대한 디맨드가 늘어날 때, 자, 사람들이 전부 다 은행에 돈을 맡기고 싶어요. 그러면 은행은 이자율을 내리겠죠. 따라서 when precautionary saving is high, when does that happen? When the volatility of the consumption growth is high, the risk-free rate is going to be low. And all this effect is going to be amplified by the risk aversion coefficient. 즉, risk aversion coefficient가 크면 클수록 이 precautionary savings 모티브가 더 크게 돼요. 더 크게 됩니다. Now, from the example, we saw the following things. First, the effect of the expected consumption growth. How is that going to affect the risk-free rate? 자, consumption growth가 risk-free rate를 어떻게 변화시킬까요? 앞에 있는 equation에서 제가 이미 설명을 드렸는데 let me repeat again. There's what's called the income effect. High future consumption means investors want to shift the future consumption to present through borrowing. 현재보다 미래에 더 수익이 많고 미래에 더 컨숨을 많이 할 것 같게 되면 어떻게 하겠어요? 미래에 있는 소득에 대비해서 미래에 소득이 있으니까 현재 론을 일으켜서 대출을 일으켜서 지금 컨숨을 더 많이 하겠죠? 따라서 이런 경우에 이자율이 더 높아지게 됩니다. The first effect is what's called the income effect. The high future consumption means investors want to shift future consumption to present through borrowing, which is going to create higher demand for borrowing, higher demand for loans. Therefore, risk-free rate is going to be high. RF is going to increase. There's also what's called the substitution effect. Higher interest rate means future consumption is relatively cheaper. Why? 인트레스트 레이트가 높으면 미래에 있는 컨섬션은 미래의 소비는 더 상대적인 가격이 낮게 돼요. 왜냐하면 리스크 프리 레이트가 높다는 얘기는 그만큼 디스카운트가 높아서 미래에 있는 소비량은 현재에 있는 똑같은 소비량보다 더 적게 되는 것이죠. 쉽게 얘기해서 인플레이션이 아주 높다고 생각해봐요. 미래에 있는 미래 100만 원의 소득은 인플레이션이 높게 되면 현재 100만 원의 소득보다 훨씬 더 낮은 가치를 갖게 되죠. In other words, when interest rates are high, future consumption is relatively cheaper, so investors want to shift the current consumption to the future. So therefore, the risk-free rate is also going to be high. In other words, when risk-free rate is high, then the consumption growth is going to be high. Now, the second effect we saw is the effect of the volatility on consumption growth. That's what's called the precautionary savings motive. When consumption volatility is high, 언제 그런 일이 발생한다고요? 경제가 불안할 때 consumption volatility가 높죠. 그때 투자자들은 더 많은 돈을 risk-free asset에 넣고 싶고 따라서 risk-free rate이 낮아지게 됩니다. And for the case of the power utility function, the risk aversion coefficient gamma is going to control the intertemporal substitution. intertemporal substitution이 뭐냐? 현재와 미래에 있는 consumption을 어떻게 변화시킬 것인지. Risk aversion and precautionary savings, everything is going to be controlled by the risk aversion coefficient. That is the drawback of the power utility function, and we will see how this drawback is going to be improved in other utility functions. And we will continue in the next part of the lecture.